Welcome to The Explainer. Today we are unpacking a massive systems clash that honestly affects almost every single part of our lives, from how we raise our kids to how we navigate our own careers. We're going to explore this often invisible collision between the dynamic, highly complex way that human brains actually develop and the rigid, incredibly flat way our modern institutions try to manage them. It is a fascinating story full of biological marvels and major bureaucratic blind spots. And as you'll see, artificial intelligence is finally stepping in to expose the deep friction between the two.
Here is our roadmap for today. First up, the algorithmic world. Second, how neural circuits grow. Third, the linear institution trap. Fourth, the geometry of stress. And finally, we'll wrap up with AI versus human blindness.
Okay, let's dive right into Section 1, the algorithmic world.
To really understand this systems clash, we first need to establish a baseline for how most of our modern institutions actually operate. Think about filling out a super complex tax form, or, just standing in a seemingly endless line at the DMV. You're moving through a system designed to process thousands of people in the exact same way. Harvard professor David J. Malin gives us this perfect, beautifully simple definition of the logic that powers these systems. He says an algorithm is essentially a list of step-by-step instructions for solving a problem. It just tells the system exactly what to do. Fundamentally, traditional algorithms and the bureaucracies that are built on their logic are completely linear. They execute one rigid rule after another, and they expect absolutely perfect compliance from whoever or whatever is moving through them.
To really hammer this home, Professor Malin uses this fantastic metaphor of programming a robot to make a peanut butter and jelly sandwich. If you tell a linear algorithmic system to put the bread on the plate, the system entirely lacks the common sense to pull out two individual slices. Instead, it might literally drop the entire unopened plastic bag of bread right onto the plate. It's a hilarious image, but it highlights a really profound limitation. Linear systems require intense precision and strict sequential processing. Because they are designed to follow one specific path, they completely panic and break down when they encounter context, nuance, or literally anything unexpected.
That brings us to Section 2, how neural circuits actually grow.
Let's pivot away from the rigid world of algorithms and look at the beautifully messy world of biology, specifically how brains actually construct themselves. There was this groundbreaking study published in the journal Neuroscience, where researchers analyzed the C. elegans roundworm. They mapped its connectome, which is basically a complete microscopic wiring diagram of the organism's entire brain. To pull this off, they use something called the Big Clam algorithm. It's a tool that specifically helps identify how individual neurons group together into distinct communities. And what they proved is that biological growth is deeply staggered. If you look at the developmental stages, basic survival communities mature first in the early larval stages. Movement circuits, those come online later. And finally, complex behavioral circuits only emerge at the very end of the developmental timeline.
So, the absolute crucial takeaway here is that neural circuits simply do not mature at a uniform, synchronized pace. They grow asynchronously. Functional communities mature in their own time. Think about what this means for a parent or a teacher. You simply cannot force a complex task onto a child, like advanced math or really intricate social regulation, if the underlying biological hardware isn't structurally ready. You wouldn't try to force a highly specialized software program to run on a computer that hasn't even finished installing its motherboard yet, right?
All right, moving on to Section 3, the linear institution trap.
So, what happens when a highly complex, asynchronously developing biological brain is forced into that flat, step-by-step bureaucratic system we talked about earlier? Well, it results in a massive systemic crash. On one side, we have this high-dimensional, staggered mind that's building specialized circuits at its own totally unique pace. But on the other side, we have a one-dimensional, linear institution demanding uniform development based on a standardized calendar timeline. Because these bureaucracies operate just like our sandwich-making robot, they completely lack the bandwidth to read the nuanced code of a developing mind. When a child's natural development is even slightly out of sync with the institution's flat ruler, the system doesn't know how to adapt. Instead, it frequently just pathologizes the child. The system will slap a label on them, deficient, broken, or suffering from clinical ADHD, simply because a complex, high-potential mind doesn't fit neatly into a rigid timeline.
To ground all this science in a real-world scenario, let's look at a fascinating case study of a 4-year-old boy in Nice, France. This child was what we call twice exceptional, a term used for kids who are highly gifted but might struggle with standard formats or asynchronous development. Now, this 4-year-old had already mastered complex verb tenses, including the notoriously difficult subjunctive mood in French. He had the math and reading skills of a first grader. And yet, his nursery environment forced him straight into their linear template. While his brain was completely ready for advanced problem solving, his school required him to sit quietly and trace dotted lines. It was the equivalent of just dropping the whole bag of bread on the plate. When he couldn't engage with this menial task, the friction became so incredibly intense that he actually began hiding his advanced abilities just to cope with the institutional mismatch.
The head teacher of the boy's subsequent school shared a really devastating quote regarding his former nursery teacher. She said she spent entire mornings telling him in front of everyone he was bad and couldn't do anything. It's heartbreaking, honestly, but it starkly illustrates the visceral emotional cost of what we call school shock. When an educator demands low-bandwidth compliance and cannot understand or adapt to how a child's brain is uniquely wiring itself, the psychological toll on that child is just immense.
Now, let's get into Section 4, the geometry of stress. If this kind of cognitive friction was constantly happening beneath the surface, how can we actually detect it before it causes permanent damage? Well, a really groundbreaking study from Stanford University, published in Nature Mental Health, offers an unbelievable methodology. Researchers recorded interviews with over 200 children aged 9 to 13 who were asked to describe stressful events in their lives. Then, they used artificial intelligence language models to transcribe and meticulously parse the sentence structure of these interviews. The goal here was to see if the AI could find hidden early warning markers in the transcripts that would accurately predict the onset of anxiety and depression years later. Now, what's really interesting here is the biggest surprise of the entire study. The absolute strongest predictor of a psychological breakdown wasn't the terrible events the children were describing at all. It wasn't the content of their stories. It was the microstructures of their language. The AI discovered that the heavy structural use of small connecting words and prepositions, literally just everyday words like and, but, and towards, was the single most accurate predictor of future trauma. This phenomenon represents something we can call forced alignment. For a gifted or stressed child stuck in a rigid system, these small connecting words are essentially linguistic scaffolding. Because they feel so out of sync with their environment, they're constantly running this internal compilation loop, desperately trying to build verbal bridges just to explain themselves. They are attempting to align their high-dimensional internal reality with a flat, one-dimensional, and honestly often broken external environment. And all of those verbal micro-adjustments, they leave a permanent mathematical signature of chaotic stress right in the very geometry of their speech.
Now, while the subtle structure of speech was the primary indicator, the actual content of the kids' stories absolutely still matters. The highest risk factor for later psychological damage was the feeling of structural social exclusion, that overwhelming, heavy sense that the entire school or system is fundamentally against you. Conversely, resilience markers were strongly present when children spontaneously mentioned their support systems. That could be playing sports, joining clubs, or talking to therapists. So the actionable takeaway for all of us is super clear. Connection is the ultimate defense against institutional friction.
And that brings us to our final section, AI versus human blindness. You really have to ask yourself, why did human professionals, smart psychologists, teachers, and administrators miss these subtle signs of cognitive friction for so long? Well, when human experts assess a child, the process is incredibly lossy. Think of lossy compression like saving a low-resolution copy of a beautiful, highly detailed photograph. You just lose most of the important data. Human experts unintentionally compress a nuanced hour-and-a-half narrative into a single, flat diagnosis, which is usually heavily influenced by their own linear templates. AI, on the other hand, acts as this flawless, unbiased eavesdropper. It retains all the microstructures and geometric nuances of speech without dropping any data. It is inexpensive, highly scalable via a simple smartphone app, and capable of detecting structural stress literally years before clinical symptoms ever manifest in a child.
Which leaves us with this final, profound question to consider today. If an AI can accurately read the complex, asynchronous biological code of a developing mind, why on earth are we still forcing our children into linear institutions that can't? It is a stark reminder that as our understanding of neurobiology and technology advances, the basic design of our everyday bureaucracies desperately needs to catch up. Thank you so much for joining me for this explainer, and remember to keep questioning the systems around you.